So we all know about the mean ergodic theory, right? It says that if you have a measure presuming system, then you can look at the iterate of a function, then this average converges in the R2 sense. So all the limits in this talk will be assumed to take in the R2 sense. And if the transformation is ergodic, then we can say more about the limit, right? We know this limit, which sometimes called to be the time average, converges to the space average, which is the integral of the function. And actually, this is not one direction, it's a if and only if. Namely, if you have a system where the space average always converges to the time average, then that would imply that T is ergodic. And in multiple ergodic averages, we are interested in like more complicated expressions. Like we could take the products of functions with different iterates. And the well-known result of Hos and Kra in 2005 shows that this R2 limit exists. And this type of limits are also related to the like summary type of problems, right? And also we can do things more complicated where instead of having a single transformation, I could have multiple transformations by which are commuting with each other. So again, in this talk, if I don't say anything about the transformation, I assume that they commute with each other. So, and we could do things even more complicated where we could, at each term, we have products of transformations and the iterates, instead of having linear iterates, we could have polynomial iterates. And thanks to the result of Walsh, we know that even the most complicated case, the R2 limit exists. So out of these limits, we know their existence. So the next question would be, what can we say about these limits? And in particular, one interesting question would be, when will this, let's call it to be the time average of multiple transformations converges to the space average? And here, the best candidate for space average would be the products of the integrals of the functions, right? So one of the sample case would be, let's look at this case. So one could formulate a question like this. So if I look at the products of different transformations with linear iterates, under what condition can we ensure that this limit always converges to the product of the integral? And if you want to reformulate this question a little bit, we could say that we look at the product transformation T1 cross T2 cross TD on the product system X to D. This question is the same as asking that when is this transformation ergodic with respect to the diagonal measure on this space. So this question was studied in a paper of Barron and Bergelsen in 1984. They actually gives a necessary and sufficient characterization for this property to be true. So they showed that the answer to this question is affirmative if and only if both of the following two conditions are satisfied. The first condition is that if you look at the difference between two transformations, it has to be ergodic for any different pairs I and J. The second condition is that if you look at the product transformation, then it needs to be ergodic with respect to the product measure on XD. So the difference between the second condition and the problem itself is that one of them is with respect to the product measure and the other is with the diagonal measure. And so it's worth noting that so these two conditions, they are, I would call them to be spectrum conditions, in the sense that if I know all the eigenvalues of the system, then I could check by hand whether both of these conditions are satisfied. Whereas this question itself, the original question, just by knowing the spectrum condition for the system does not immediately give you an affirmative or negative answer to this question. So that's the difference between the product measure and the diagonal measure. Okay, and in order to formulate our questions more conveniently, we will need to introduce some annotations. So in our setting, when we say something is a ZD system, we mean a tuple like this, where XB mu is a probability space, and this Tn, this is a group, a ZD group action of measure presuming transformations acting on the space. And sometimes for convenient, when writing a Z or ZD system, we do not write the entire group here. So sometimes we just write the generators. So if a group is generated by T, we write a Z system like this. And for ZD system, instead of writing on the entire group, I write down the generators T1, T2, and TD, and we still call them to be Z or ZD systems. Okay, and now let us assume that I have some functions P1 to Pk, which are maps from Z to ZD. And we say that a sequence, so this tuple of functions is jointly ergodic with respect to the measure mu, or with respect to the system. It's the same thing. If for any L infinity function f1 to fk, I look at the average, the multiple ergodic average with respect to the iterates p1n to pkn. So here we are in a ZD system. So the input is an integer, so the output is a d-dimensional vector. So this average will always converge to the product of the integral. If that's the case, we say that this tuple is jointly ergodic for this system. So then, motivated by the result of Burgos and Behrend, we could ask a more general question, namely, if I have a tuple of functions and I have a system, why is this tuple jointly ergodic with respect to the given system? And so based on the result of Behrend and Bergelsen, we could make some natural conjectures on it. But in order to formulate the conjecture, I will need one more definition. So suppose I have a ZD system and I have a sequence of d-dimensional vectors. I say that this sequence is an ergodic sequence with respect to the system if whenever I have a function f and I look at the single time average for f along this sequence an, if this sequence always converges to the integral of f, then I will say that this sequence is an ergodic sequence. So one of the examples is like if we are in a Z system and T is an ergodic transformation. So by the mean ergodic theory, we know that T being ergodic is equivalent of saying, using this language, the entire sequence of integers is an ergodic sequence for the measure. So here for convenience, we don't talk about ergodicity for transformations, but we talk about ergodicity for sequences or sequences of transformations. Okay, and then inspired by the result of Behrend and Bergelsen, we could formulate the following conjecture. Suppose I have some functions P1 to Pk from Z to ZD. Let's say that they are polynomials. And then this tuple of functions will be jointly ergodic with respect to a ZD system if and only if the following two conditions are satisfied. The first condition is like you look at the difference of these polynomials, and this should be an ergodic sequence with respect to the measure mu. And the second is that you take the product of these transformations, which gives me a sequence of actions on the product system. Then this sequence should be an ergodic sequence with respect to the product measure. And again, here, these two conditions, as I mentioned, are spectrum conditions, whereas the joint ergodicity is not a spectrum condition. So this is why these two conditions would simplify the problem on characterizing whether a sequence of functions are jointly ergodic or not. So here are some results that we know in this problem. So the first result would be like Behrend and Bergelsen. So they proved that for this sequence, we have an affirmative answer for the jointly ergodicity conjecture. Yeah, by the way, so this problem, I call it to be the jointly ergodicity conjecture. And another interesting result was given by Bergelsen and Leibman. So they proved that in this case, you have two transformations with linear iterates, just two of them. But what is interesting here is that here T1, T2 are not commuting with each other. They only require the T1, T2 to form a nilpotent group. But then they can verify that the jointly ergodicity conjecture is also true in this case. There is a more recent result by Bergelsen, Leibman, and Sun. So what they can do is that instead of looking at a linear iterate, we can replace them with bracket linear polynomials like alpha of I times n, and then you take the integer part. And basically they proved that the answer to this question is also true for this tuple. So these are the examples that we have for linear-like iterates. And for nonlinear iterates, there was earlier work of Truth and Zikinakis and Host in 2011. So they proved that if you have tuples like this, where the P1 to PD are polynomials of distinct degree, then in this case, actually, we also have an affirmative answer to this question. Well, actually, in their paper, they didn't do anything about joint ergodicity, so they didn't state this result explicitly. But actually, by using the mean technical results in their paper and together with some very quick argument, it's not very difficult to show that they essentially were able to answer this question for this case. Okay, so these are the known results in literature. And in the last few years, there has been some progress in this problem, which enables us to do even more general cases. Like the result I'm going to talk in this talk would be joint work with Sebastian Donoso and Andres Kouzounasis. So we proved that for the following tuple, the joint ergodicity conjecture is satisfied. So here, what we have is that we could have T1 to a polynomial and then TD to a polynomial power, where all the polynomials are the same. So one of the example would be, we could prove T1 to the power of n squared, and then until TD to the power of n squared, which is a result that was not covered in the previous slide. Well, so after this result, there are also some further development in this direction. So a few, maybe one year later, the three of us together with Andrew Ferry, we proved a slightly more general case than this case. But I'm not going to state this result because it's a little bit technical. And in that paper, we also improved some of the technical tools in our original paper. So make them argument like more more effective in some sense. And there was a very recent result by Franzinakis and Kuka. So they were able to prove an even more general case where they can show that if you have polynomials P1 until PD, which don't have to be the same polynomial, but they can show that the joint ergodicity conjecture will be satisfied for this tuple. I think in Boris' talk at the end of this morning, he will talk about this topic. And also, there's another result by Sebastian, Andres, and I, which shows that this function P don't have to actually be a polynomial. If P is a Hardy-field function, as Tina talked about Hardy-field yesterday, which are functions like n to the power of 1.5 or say n times log n, this type of function. So we are also able to verify that joint ergodicity conjecture is satisfied for this type of tuples. So in the next talk, Sebastian is going to talk about some topics related to this project. And in this talk, I'm mainly going to focus on this result. And I will basically talk about some of the new tools that was developed in this area that can help us to answer these questions. Okay, so to begin with, I would like to take a revisit of the result of Barron and Bergelsen. So remember that they proved the joint ergodicity conjecture for these linear iterates, right? So it's this result. So the result of Barron and Bergelsen was proved in 1980s, and we know that at that time we do not have the big tools like the structure theorem, things like this in ergodic theory, and so but they managed to prove this result without using any modern tools in dynamics. So here the proof I'm going to present is a different proof, and this proof we will use the structure theorems. But here, I hope that this gives you a feeling on how all the structure theorems can be very useful in the study of this type of problems. So this is an if and only if condition, but one of the direction turns out to be not difficult, namely the only if condition. So to prove the only if condition, what we need to show is that if one of these two conditions is not satisfied, then I wanted to show that this tuple is not jointly ergodic. So if I first assume that the first condition is not satisfied, then that means I can find a non-constant function f such that t1 of f equals to t2 of f. Well, if I have a function like this, then I can, so this is the multiple ergodic average we are looking at, right? I will set all the functions starting from f3 to be the constant one function, and the first two functions to be the same function f here. Then what will this average become of? Because t1f equals to t2f, so this is the average of t1 of t1f square. And then by using the, and then by using the mean ergodic theory, by using the mean ergodic theory, we know that this one will converge to the square of the conditional expectation of f under the T1 invariant sigma algebra. But then because of the Cauchy-Schwarz inequality, we know that this could never equal to the square of the integral unless f is a constant function. But here, as I mentioned, f is not a constant function in the beginning. So this means that the space average is not always convergent to the time average. So that I should the other way around. The time average do not always converge to the space average. So this will be not jointly ergodic. So next we will need to show that if the second condition fails, then it's not the tuple is not jointly ergodic. To do that is if the second condition fails, then I can find a non-constant function g, which is invariant under the product transformation T1 cross T2 cross TD. Well, so here we actually need to make a little bit discussion here, and we need to use the spectrum theorem a little bit. But essentially, if you believe me, then this is essentially enables us to reduce to the case where G is of the form of tensors of functions f1 to ft. Well, this step is not entirely trivial, but I omit some of the details here. But the thing is that you can assume that G takes this form. And if that's the case, if I substitute the f1, f2 until ft given by the function G, then because of the invariance of the function G, the multiple ergodic average that we are looking at would be the constant, which is the product of the functions f1 to ft. And but this function will not be the same as the integral of the functions unless all the functions f1 to ft are constant functions. But this would imply g is a constant function. So that means if the second condition fails, then the tuple is also not jointly ergodic. Mm-hmm. Yes. In the last line, I'm not taking the average on the tensor product of f1 to fd. I'm taking the average along the products of f1 to fd. Oh no, in the last equality, I'm only using the fact that this f1 to fd are invariant under the transformation. Uh-huh. Uh, uh, yeah, yeah. So the it is like the f1 times f2 times fd that you see there. This is not a function on x to the d. This is a function on x. This is the function f1x times f2x until. Uh, Uh, yeah. Yeah. It's like yeah. So basically yeah. You indeed need to be a little bit careful when passing from the product measure to the diagonal measure. But in this case, actually, actually it's easy to pass there. So this is not the problematic part. Yeah. Yeah, but the key point is that the only if part after some discussions, you have to be a little bit careful, as Vitaly mentioned. But after some careful work, you can show that this direction is not quite difficult. And basically, the main part would be the if part. And in order to talk about the if part, I will need to introduce some of the notations regarding to the whole square seminops and whole square measures, and which we have heard a lot in the last 2 days talks. But in our case, the definition is slightly different. So suppose we have a GD system, XP mu Tn, and let us assume that G is a subgroup of GD. And then I use the notation IG to denote the sigma algebra, sub-sigma algebra of all the G invariant sets. And whenever I have a sub-sigma algebra D of B, then I can define the relatively independent product mu cross mu under D. So this is given by the formula that I mentioned there. So you look at the conditional expectation of the function f and g under that sigma algebra, and then you take the product. So this is the what we call the relatively independent product. And then we could use these concepts to define whole square measures inductively. So let us assume that I have some groups G1, G2, and GD, which are subgroups of GD. So the first measure, mu G1, is defined to be the relatively independent product of mu cross mu under the G1 invariant sigma algebra. And then I can do it inductively. And suppose I have defined the D-1 step whole square measure. Then the next step is defined to be the self product of the previous step conditionally on the invariant and sigma algebra under GD delta. And what is this GD delta here is that this is the diagonal group generated by all the elements coming from GD. And the dimension of the diagonal is 2 to the power of D-1. So inductively, this defines a sequence of measures like mu G1 to GD on the power space x to the power of e to the 2 to the power of d. And then we could use these measures to define seminopes. So for any function f, say it's an L infinity function, I can define the whole square seminome of f with respect to the groups G1 to GD to be the following one. So this is the integral of the tensor product of f with itself for 2 to the power of d times, where the measure that we put here is the whole square measure that I just defined on the previous slide. So the whole square seminome that I defined here is different from the one that you see in the previous 2 days, in the sense that in the previous 2 days, what happens is that all the group G1 to GD, they equals to the largest group. So in our case, it should be like all these G1 to GD are the entire group GD. But in our case, at a different step, we could put a different subgroup. So this is like in the dynamical cubes, it's like in the one direction, you can go with the group G1, but in the other direction, you can go with a different group G2. So it's like at different direction, you can go with different groups. And so this is the our seminome. And this type of seminome is very useful in providing an upper bound for multiple ergodic averages. For example, there is a result by a host, which shows that for the multiple ergodic average for linear equations for commuting transformations, you can bound this thing by the whole square seminome of F1 with respect to the transformations that I listed there, these transformations. So this result is a direct application for the Van der Kolk trick, and together with the unpacking the definition for the Host-Croix seminar. Yeah, but a bad thing about this type of factors is like, if the groups G1 to GD are different, then in general, we don't have a very good structure theorem, in the sense that the structure part is not a new system or a function coming from new system. And in this case, there are a few results by Austin and the host on this type of structure theorem, but we know that the structure is very bad in general. But in terms of the joint ergodicity problems, we can cheat a little bit here. The reason is that it's given by the following corollary. It turns out that if I know that all the relevant transformations in the that defines the Host-Croix seminar are ergodic, then we could replace those transformations by the entire group GD. Then so basically the corollary says that if we can, if all the transformations T1 and T1 TJ inverse are ergodic, then I can bound the multiple average by the conventional Host-Croix seminar with the entire group GD. And for that group, we know that nowadays we do have a good Nilpotent structure for that seminar. Okay, and so the next thing that we need to talk about is that there is a recent work with of Franzikakis, which gives us a very nice criterion for jointly ergodic, for characterizing when a sequence of functions are jointly ergodic. So in Sina's talk at the end of yesterday, he also mentioned this result. But here we are talking about a ZD version of it. So the ZD version was generalized by Best and Ferry later. So it says that if I want to check a tuple P1 to PK is jointly ergodic, I only need to check two conditions. The first is called the good for seminorm estimate condition. Namely, I wanted to show that the multiple ergodic average I'm looking at equals to 0, provided that the Host-Croix seminorm for any of these functions with respect to the group ZD equals to 0. So that's the good for seminorm estimate, which essentially allows you to reduce the problem to the Nilpotent case. And then the second condition is to say that you actually don't need to check the Nilpotent case. You just need to check the rotation case. So the second is the good for equidistribution condition, where we need to check that basically the time average converges to the space average for all the functions which are measurable with respect to the largest rotation factor of x, or in other words, the Kronecker factor of x. So basically, the second thing tells you that it's sufficient to verify this result for rotation systems. So these are the two things we need to verify. So now let's go back to the result of Barrett and Bergelsen. So we are now ready to prove the if condition. So so there's two conditions, right? One is the red condition, and then there's a blue one. So I put them in colors so you can see it more clearly. First of all, about the good for equidistribution condition. It turns out that the blue condition would always imply good for equidistribution. The reason is that if we are in a rotation system, then an orbit in a torus is, if it is equidistributed at one point, then it is the same as saying that it's equidistributed at every point. This is because of the homogeneity of the torus. If you move the initial point, you are not going to change the equidistribution properties. And that means for rotation systems, being ergodic with respect to the product measure is really the same as being ergodic with the diagonal measure. So therefore, for rotation systems, you get the joint ergodicity for free from the blue part. So that means the blue condition gives us the good for equidistribution. And then what we want is the good for seminorm control property. And recall that I talked that the host gives us an inequality where I can bound the desired average by a host cross seminom like this. And then the next corollary says that if all the transformations that you see in the host cross seminom are ergodic, then I can replace the seminom bound by the group by the ZD norm like ZD, 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 so on. And this would be so if this is the case, then we would have that it's good for the seminom control. And in this case, it turns out that we indeed have that these transformations are ergodic. The reason comes from the red condition, because the red condition tells you that T1 Tj inverse is ergodic. The ergodicity of T1, though, it doesn't quite follow from the red condition, but it is hidden implicitly from the blue condition. Because the blue condition says that the product sequence is ergodic. So that means that if you restrict yourself to the first product, first coordinate is ergodic. So in particular, T1 is ergodic. So that means we can apply this corollary to show that it's also good for seminorm control. So that means both of the conditions are satisfied, and this would imply that the sequence T1 until TDN is jointly ergodic. So this is a proof of the result of Burgos and Behrendt using the tools that's developed in the recent years. Yeah, that's a good question. Probably there's a power there. And also, actually, in the more general polynomial case, what we are it actually what we have is a weaker version for it, in the sense that we prove that if the right hand side is 0, then this would imply the left hand side is 0. Like in the here it says if that seminom is 0, then we have this is 0. I see. Yeah. I see. Yeah. For the linear case, it's yeah. I think it seems a nicer compared with the polynomial early. Okay. So now so much for the result of Burgos and Behrendt, and let us look at like one example that for the new result, namely, let us consider the tuple where we still have T1 to TD, but now the polynomial is n squared. And we wanted to verify the joint ergodicity problem in this setting. And again, the only if part of this theorem is very similar to the philosophy that I mentioned before. So this part is relatively easy. Well, indeed, you need some work to deal with the spectrum of the system. But if you trust me, this is not the difficult part. So now let's look at the if part. For the if part, again, so we need to verify two things. The first is good for equidistribution. For the good for equidistribution, this is very similar to the previous part, that in the sense that this is guaranteed by the blue condition. This is again because if you are in a rotation system, even for polynomial iterates, then being equidistribution with respect to the diagonal measure is the same as being equidistribution for the product measure. So the major difficulty is to verify the good for seminorm estimate condition. Namely, I wanted to show that the average I'm looking at converges to 0 if the host cross seminorm for, let's say, F1 with respect to certain ergodic transformations S1 to Sk equals to 0. And the conventional way that we want to find out our upper bound is to use the Będlewo trick, which Sohail had a very good talk on this trick in the on Monday. But one bad thing about the Będlewo trick is that the Będlewo trick works very nicely for linear iterates and also for polynomial iterates, but for single transformations. If you want to use directly the Będlewo trick for multiple transformations, you will not get as nice estimate as we get before. Because if you look at the inequality of host, you can bound this average by a single host cross seminar, right? But if you try to do the same thing for our case, as you can see, the right-hand side is not a single host cross seminar. So this is a triple average for host cross seminars of F1, where the transformations that defines the host cross seminar, which I wrote by SH1 until SH7, they are transformations that is dependent on the parameter capital H, which is H1, H2, H3. And actually, you can compute out these transformations S1, SH1 to SH7 explicitly. So they can be written like this. So here, for convenience, I use the notation R to denote the transformation T1 times T2 inverse. As you can see, for example, if you look at SH3, let's say, so if you, for different choice of H1 and H2, these would be different vectors pointing to a random direction in the Z2 space. So for different H, you will have different seminars. And so basically the difficulty here is that we don't really have a single host cross seminar estimate. And in order to overcome this difficulty, what we use is a work of Tau and Ziegler on concatenation theorem. So the theorem itself is a little bit difficult to state, but roughly speaking, it says that if you wanted to estimate the average of multiple host cross seminars, then you could this machinery enables you to add the groups in different seminars together into a larger group. So there are many different versions of concatenation theorem, and the one that we use here is the following one. So suppose I have a finite set of index I, and for each index and each j from 1 to k, I have some subgroup hj, ji. I wanted to look at the average of the host cross seminar of F with respect to the h1i until hki. And in order to show that this average equals to 0, it is sufficient to show the first line, namely I take a double average on I and I prime, and for each I and I prime, I look at a host cross seminar, but the groups given by the host cross seminar are the sums of those hji and hj prime and I prime. So if I can prove that this average is 0, then the target average will be 0. So what's the difference is that in the original average, we have a k-step host cross seminar, whereas when you take a double sum, you have a host cross seminar of k-square steps. So you significantly increase the length, the steps of the seminar. But what you can gain from here is that you are able to take the sums of the subgroups, and taking the sums usually would give you a larger group. And if you have a larger group, in the end you will actually end up with a better structure theorem. So this is the use of it. Like one of the example would be, let us consider the case where the 7 groups are given by the SH1 to SH7 that I defined there. If we use the concatenation theorem, for example, this would allow us to take the sum of different groups. Say that if I take the sum of, let's say, SH3 and SH5, but possibly for different H, then what is it? So H3 is like you are pointing in one direction depending on H1 and H2, but for H5, you are pointing in a different direction. But generically, if you choose your these two H sufficiently independent, this is like 2 vectors in Z2 in different directions. And the group generated by like the sum, if you take the sum of these groups, this is like a finite index subgroup of the entire Z2, entire group Z2. It is exactly because of this reason. So if you start by adding the groups together, you will make the group larger and larger, and then you will get a better seminar estimate. So if we apply the concatenation theorem in our to our case, we would able to show that I can bound this average seminorm by a single large seminorm. And the large seminorm will have 49 terms because you have 7 to the you have the square of 7, so this many terms. You have many groups here, but the good thing is that these groups, G1 to G7 that I write there are only 2 possibilities, 3 possibilities. The first is that it's a group generated by T1. Well, it's a finite subgroup of the group generated by T1. And the second is a group generated by R, which is the T1, T2 inverse. And finally, some of the groups will become very large. It is the group generated by T1 square and T2 square, which is a finite index subgroup for the G2 group. So therefore, but on the other hand, so if the action T1 and R are ergodic, and this is if that's the case, then on the right hand side, I can further replace the group G1, G2, G4, and G6 by the whole group G square. And if that is the case, then we would have the good for seminorm estimate condition that we are looking for. And what about the transformation T1 R, and are they ergodic? And the answer is yes, because the ergodicity of the transformation R, this is exactly given by the red condition there, because the red condition would imply Ti Tgen inverse is ergodic. And the ergodicity assumption on T1, this is hidden implicitly in the blue condition, because if you project to the first condition, first coordinate, you will see that T1 is ergodic. So basically, in conclusion, we have that we indeed have the good for seminorm estimate condition. So putting everything together, we have that the tuple T1 square and the T2 square is jointly ergodic for the system. So I hope that this example explains that the difference between the polynomial case and the linear case, and how the concatenation theorem is very useful here. In the last 2 minutes, maybe I can mention an additional difficulty for the general jointly ergodicity conjecture. So think about the question where, consider we have again a pair which is T1 and T2, but instead of having n squared, we have n cubed. So what can we do in this case? So even though the van der Kolk trick tells us that we can always reduce a polynomial pattern into a linear one, but the amount of computation is enormous. And if you pass from n2 to n squared, you will increase the amount of computation significantly, and it will be almost impossible to write down an expression. But as we discussed before, if we want to use the concatenation theorem, we have to first compute explicitly the subgroups SH1 to SH7, right, in order to talk about their sums. So in the general case, these groups SH1 to SH7 will be very difficult to compute, right? So in this case, how should we apply this concatenation result and the van der Kolk? So the solution to this is that we are unable to compute them explicitly. So we invent some method called the coefficient tracking method. So this is a method that enables us to, instead of computing the van der Kolk trick step by step, I'm going to record some information on the coefficients of the polynomials on each step. And that information, even though it don't give me the full description of the computation, but it is some some information which is sufficient for us to deduce a good seminorm estimate. So this is actually another difference between the van der Kolk for single transformation and for commuting transformation. For single transformation, you just do the pattern induction. You don't care about the coefficients of the polynomial, because in the end, you will always get a linear iterate. But for commuting transformations, because we have to use the concatenation theorem at the end of the day, which is relevant to the coefficients. So we have to be very careful about the coefficients when we are doing the induction. So this is why that we have to keep track of the coefficients. Okay, that is all that I have. Thank you very much for your attention. Yeah, so it's like in one of our previous version. So what we are doing is that we are not using the Francis criterion. So basically what we do is like, for example, if I have a corollary like this, the last line, then I can decompose F into two parts, the structure and the random part. So for the structure part, I can assume the system is a nilpotent system. So then what we are going to do is that it's sufficient to prove joint ergodicity for nilpotent systems. But then it turns out that there is a very subtle thing on talking about equidistribution for nilpotent cases. It's like if the group G is connected, then I think everything works well. But if G is not connected, there are some additional issues you need to overcome. So this, but so to sum up, that means there are still some obstacles if you want to do the nilpotent case. And what we are doing here is that instead of working actually on the nilpotent case, we use the criterion of Francis, which tells you that if you are working for joint ergodicity problems, you don't have to think about nilpotent case. You can reduce everything directly to the rotation case. But for the rotation case, everything is much easier. This is also a mystery to me too. It is a very nice result, but I think using some ideas from analysis, but somehow that he's managed to reduce to the rotation case without actually using any structures for the nilpotent or theorems regarding to nilpotent systems.